Over the past few lectures, we've developed the machinery necessary to solve the time-independent Schrödinger equation with a potential given by a delta function. We've talked about bound and scattering states, and the delta function potential will actually have both solutions, or both types of solution. And we've talked about boundary conditions, which will help us match solutions in the areas away from the delta function, where we can easily express the solutions, we'll be able to make those solutions match at the delta function itself. So, what we're working with is a delta function potential, v of x, and v of x under these circumstances looks something like this. It's 0 everywhere except at a specific point. So we're looking now at v of x as a function of x. It's 0 everywhere except at the origin here, x equals 0. And there, it goes to negative infinity. I'm defining v of x to be minus a times delta of x because we don't necessarily know exactly what the strength of this delta function potential is. You can have different strengths of delta function. If you treat a delta function as a distribution, of course, it has to be normalized. But in this case, we're treating it as a representation of a potential. So we need some constant here which determines the strength of the potential relative to sort of a unit normalized potential. What our solutions will look like under these circumstances depend on the energy of the solution. For instance, if we have an energy up here, E greater than 0, we know we have, in these regions away from x equals 0, we know we have sort of traveling wave solutions. We don't know exactly what happens at x equals 0 here, but we know these are going to look like solutions to our free particle potential, which we discussed a few lectures ago. On the other hand, if we have an energy below 0, then we know what the solutions have to look like. When our energy is below our potential, our solutions have to curve away from the axis. And if we're going to have something normalizable, we need to have the solutions eventually, as they curve away from the axis, instead of curving up to infinity or curving down to minus infinity, they have to just sort of smoothly join in with the axis itself. And we have to have that on both sides of the boundary. But we still don't know what exactly happens at the boundary. That's where our boundary condition matching comes in. But first of all, let's consider what the solution looks like away from the boundary. And in this lecture, I'm going to focus on the bound state, the state where the energy of the state is less than 0. For the bound states, energy less than 0, if what we're looking at is away from x equals 0, then we know v of x is equal to 0. So our time-independent Schrödinger equation becomes minus h bar squared over 2m times the second derivative of psi with respect to x is going to be equal to E times psi. We know the energy now is negative, so we're going to have a negative quantity on the left and a negative quantity on the right. In order to consolidate some constants, let's consider moving the 2m over h bar squared over to the right-hand side here by multiplying through 2m over h bar squared. We'll end up then with d squared dx squared of psi is equal to k squared psi, where I'm defining k to be equal to something that looks a little strange, square root of minus 2me all over h bar. To make the signs clear here, energy is negative, so what we're actually looking at here is the square root of a positive number. We've got a negative energy, positive mass, and negative from the minus sign, negative from the energy. So we're taking the square root of a negative quantity here, so our k constant here is going to be real. Looking at our equation here, you can look at this and think second derivative is giving me something squared times my wave function back. Well, I know what the solution to that sort of differential equation is. It's psi of x is equal to a e to the minus kx plus b e to the kx. This is our general solution, and as is typical in quantum mechanics, if what we're going to have is normalizable, then we can set some conditions on this. Our actual space looks like this. We have, as a function of x, our potential is blowing up at x equals 0. So we know we have a solution away from x equals 0. That's what we're trying to find here. If we want a solution on the right here for x greater than 0, and we want our wave function to be normalizable, we know we have to have b equals to 0. Because if we have a non-zero b, integrating, say, the squared modulus of the wave function from 0 to infinity will give us infinity, because we have something growing exponentially here. So for x greater than 0, we know b must be equal to 0. Similarly, for x less than 0, we have to have a equal to 0, because otherwise we have something growing exponentially as x goes to minus infinity. What our overall solution then will look like is in region 1 here, let's say psi 1 of x is going to be equal to a times e to the minus k, or to the e to the kx, whereas in region 2 we're going to have our solution psi 2 is equal to b e to the kx with the minus sign. So e to the minus kx over here, e to the kx over here. What our solution then is going to look like overall is something like this and something like this. And we still don't know exactly what happens at the boundary. So let's figure out what actually happens at the boundary. Our boundary conditions, and we had two of them, was first of all that psi was continuous, and second of all that the first derivative of psi was continuous unless the potential went to infinity. Let's consider the first of those boundary conditions here. Psi continuous. In order to have psi continuous, what this means is that in our regions here we have psi 1 on the left and psi 2 on the right of x equals 0 here. If we're going to match these two conditions continuously, we have to have psi 1 of x equals 0 equal to psi 2 of x equals 0. If I evaluate my solution on the left at the boundary and my solution on the right at the boundary, I have to get continuity, I have to get equality. So if we go back to our general solution, we had our psi 1 was, flipping back a slide a moment to get my a's and b's straight, our psi 1 was a times an exponential growing with x, and psi 2 was b times an exponential decaying with x. So going forwards a slide, our solution in region 1 is a e to the kx. If I'm evaluating that at x equals 0, I have to get something that's equal to b times e to the minus kx evaluated at x equals 0. Now when I evaluate the exponential parts here at x equals 0, I'm substituting in 0 in the exponent. Anything to the 0 is 0, or sorry, is 1. So both of these terms become 1, and I'm just left with a equals b. That helps a lot, but it doesn't tell us everything. Our second boundary condition was that the first derivative of the wave function, d psi dx, was continuous. But it's actually not continuous in this case. We had a condition on this boundary condition. We can only apply this boundary condition when the potential remains finite. And in this case, we have a delta function potential at the origin, so we're going to actually break this boundary condition in this case. We're not going to break it beyond all hope of recovery, though. The question is, what does d psi dx do at the boundary? The way to solve this problem is to go back to the Schrodinger equation, the time-independent Schrodinger equation, and keep in mind that our potential now is delta of x. It's a delta function. We actually had a minus sign and an a in front of that. So if we go back and think about what happens with delta functions. Delta functions are only really meaningful when you treat them as distributions and integrate. The trick here, then, is to think about integrating the Schrodinger equation. Where does it make sense to integrate the Schrodinger equation? Well, I don't know anything about the solution. Well, I know everything about the solution away from the boundary, but I don't know what happens at the boundary. So let's just integrate over the boundary. Let's integrate from, say, minus epsilon to epsilon, just integrating over the boundary. To rewrite that, what we've got is minus h bar squared over 2m times the integral from minus epsilon to epsilon of second derivative of psi with respect to x squared. That's our first term. Then substituting in for our delta function, we have minus a integral from minus epsilon to epsilon of delta of x psi of x. And then on the right-hand side, we have an integral from minus epsilon to epsilon of energy, which is a constant and can come out, psi of x. All of these integrals, and I've left them off all over the place, are taken with respect to x. So we have three separate integrals here, and we can figure out what each of these terms look like. Our left-hand term, we have the integral with respect to x of a second derivative. So that's easy. We're just going to get the first derivative. Minus h bar squared over 2m times d psi dx evaluated at the endpoints, epsilon and minus epsilon. So far so good. The second term here, we have minus a, and now we just have a delta function in an integral. Delta functions just pull out the value of whatever else is in the integral wherever the delta function, or wherever the argument of the delta function goes to 0. In this case, delta of x is going to pull out the x equals 0 value of psi. So this is just going to give me psi of 0. On the right-hand side here, I'm going to get something. But the key point about this integral is that we're only integrating over the boundary. We're going from minus epsilon to epsilon. You can probably see where I'm going with this. I'm going to let epsilon be a very small number. As minus epsilon goes to epsilon, or as epsilon goes to 0, I'm essentially integrating this function psi from 0 to 0. So I'm not going to get anything meaningful here. I'm just going to get 0. So this is actually all right. What we've gotten from consideration of integrating the time-independent Schrodinger equation over the boundary with the delta function potential is a condition that tells us how much our first derivative changes at the boundary. If I rearrange the expression, this expression here, I'm getting derivative of psi with respect to x evaluated at epsilon minus what I get if I evaluate it at minus epsilon. That's just equal to, rearranging my constants, what is it going to be equal to? Minus to 2ma over h bar squared times psi of 0. So that's actually pretty nice to work with. Let me try and move this over a little bit to give myself more space to work. And what we're left with then is substituting our general expression for our solutions for psi, now away from the boundary, into this expression. So we had d psi dx, evaluating this at positive values of epsilon, means I'm in region 2, I'm on the right, which means I'm working with psi 2, evaluating that at x equals 0 on the boundary, subtracting d psi 1 dx, evaluated at x equals 0. So for now I'm letting epsilon go to 0, and I'm looking at just the values of the first derivatives. This is our left-hand side over here. We can substitute in values for that because we know what these expressions are, and furthermore, we know that a is equal to b in our expressions for the general solution. So if you refer back to our definitions earlier, what you get here, you're taking the derivative of an exponential, which brings down the k, and we get minus bk e to the minus kx, and we're evaluating this e to the minus kx at x equals 0. So this e to the minus kx is just going to go to 1. So I'm not going to bother writing it. I just get minus bk for the first derivative of psi in region 2 at the boundary. For the first derivative of psi in region 1 at the boundary, now I'm subtracting it because this is the second endpoint. I get a very similar expression. Again, bk e to the now plus kx. And again, evaluating this at 0, means my e to the kx is just going to be 1. The right-hand side now, we had constants minus 2ma over h bar squared, and then the value of psi at 0, is just going to be b e to the plus or minus kx. Again, substituting in x equals 0. It doesn't matter if I'm considering the plus or the minus, region 1 or region 2. This is still going to be just 1. So far so good. I can cancel out all of my b's. And what I'm left with, when I simplify a little bit, is minus 2k being equal to minus 2ma over h bar squared. This is the sort of condition we got when we were looking at how the boundary conditions affected the solution to the particle in a box potential, the infinite square well potential. When we actually looked at what the boundary conditions required, and in the case of the particle in a box, it was that the wave function went to 0 at the endpoints of the box, we got quantization. We have quantization again here, except we have a strict equality. There are really no more unknowns in this expression. If you manipulate this further, k equals ma over h bar squared, keeping in mind that k is equal to the square root of minus 2me, where e is a negative number, over h bar, you can solve for the energy. And what you get is that energy is equal to minus ma squared over 2 h bar squared. We have quantized energies. What our wave function then looks like, so far, what we know is that psi of x is equal to, on the left, e, and now substituting back in to the definition for k, e to the ma(x) over h bar squared, if x is less than 0, and e minus ma(x) over h bar squared, if x is greater than 0. Now, all of this had a b multiplying it out front, which I canceled out here. So my first derivative boundary condition did not help me find b. But there's one more fact that we know about wave functions like this, and that is that the wave function has to be normalized. So if you want to normalize this, you calculate the normalization integral, which you all should know by now. Integral of psi star psi dx has to be equal to 1. You can substitute in this definition for psi, set it equal to 1, do the integral, and find out what b is. This was one of our activities on day 4, so refer back to day 4 if you want to see a little bit about how to normalize a wave function like this. To summarize our results, this is what our normalized bound state solution actually looks like. What you find for the normalization constant is the square root of ma over h bar out front. And now instead of writing it as a piecewise function for positive and negative x, I'm expressing this as an absolute value of x in the exponent. The energy associated with this was minus ma squared over 2h bar squared. We are quantized, but we only have one bound state solution, singular, and this is what it looks like. For a delta function potential, you get these two exponentials decaying as x moves away from the origin. To check your understanding, consider the following two questions. Why is there only a single bound state? And can any initial condition be expressed as a superposition of bound state solutions in this case? V of x, and V of x under these circumstances looks something like this. It's 0 everywhere except at a specific point. So we're looking now at V of x as a function of x. It's 0 everywhere except at the origin here, x equals 0. And there it goes to negative infinity. I'm defining v of x to be minus a times delta of x because we don't necessarily know exactly what the strength of this delta function potential is. You can have different strengths of delta function. If you treat a delta function as a distribution, of course, it has to be normalized. But in this case, we're treating it as a representation of a potential. So we need some constant here which determines the strength of the potential relative to sort of a unit normalized potential. What our solutions will look like under these circumstances depend on the energy of the solution. For instance, if we have an energy up here, E greater than 0, we know we have, in these regions away from x equals 0, we know we have sort of traveling wave solutions. We don't know exactly what happens at x equals 0 here, but we know these are going to look like solutions to our free particle potential, which we discussed a few lectures ago. On the other hand, if we have an energy below 0, then we know what the solutions have to look like. When our energy is below our potential, our solutions have to curve away from the axis. And if we're going to have something normalizable, we need to have the solutions eventually, as they curve away from the axis, instead of curving up to infinity. Over the past few lectures, we've developed the machinery necessary to solve the time-independent Schrödinger equation with a potential given by a delta function. We've talked about bound and scattering states, and the delta function potential will actually have both solutions, or both types of solution. And we've talked about boundary conditions, which will help us match solutions in the areas away from the delta function, where we can easily express the solutions, we'll be able to make those solutions match at the delta function itself. So, what we're working with is a delta function potential. You're curving down to minus infinity. They have to just sort of smoothly join in with the axis itself. And we have to have that on both sides of the boundary. But we still don't know what exactly happens at the boundary. That's where our boundary condition matching comes in. But first of all, let's consider what the solution looks like away from the boundary. And in this lecture, I'm going to focus on the bound state, the state where the energy of the state is less than 0. For the bound states, energy less